All right. So if you noticed in Blackboard, I put a whole lot of stuff related to my classes, 112 and 114. So there's a lot of the PowerPoints that are available there to you. This one is in there. This is like, we're going to go back to the first week. It's like speed dating. Okay, we're fixing to have like a speed dating session. We're going to go back to the very beginning and just zip through all of this. Again, this is available on Blackboard, and like an outline that you can use to sort of follow along is also on there available to you. So, let's see if you want clickers in here so I can sit down and listen.
He was using it.
Ethan was using it?
Yeah.
Hang on. You just got to recognize it. Hold on. What is well, anyway, it's not going to work for me. So, okay. Okay. So, production of X-rays. There's basically 4 events that have to occur in the X-ray tube to produce photons. So, somebody tell me what they are. What's the first thing that has to happen? Say it loud. You have to have a source of what?
Yes,
Electrons. We have to have a source of electrons. So we have to have the boiling off of the filament, right? Okay. Then what happens in the tube? So we have these electrons that are being boiled off. Then what happens? They get focused, right? And then what?
acceleration.
Yes, they get accelerated rapidly across the tube to the anode. And then what?
Rapid deceleration.
Yes. So then there's a sudden stopping of them. So those are basically the 4 events that have to occur in the tube to get X-ray photons produced. So what do we call the release of electrons from atoms in the filament? Thermionic emission. Yes. These are just basic terms that you've got to know. Okay. What's the filament made of? Tungsten. So these electrons must travel from the cathode to the anode at a great speed. What charge is the cathode?
Negative.
Negative. And what speed do these electrons generally travel? Half the speed of light. The photons are what always travel at the speed of light. So those electrons going from the cathode over to the anode, it's about half the speed of light. And that's determined by what setting on the control panel? KBV. Yeah, it's going to determine the speed at which those electrons travel across the tube. So they have to be, the electrons have to be focused to help them hit the anode in a small area. What is the actual place that the electrons hit on the anode called? The target. And the size of that area is called the focal spot and is determined by the size of the filament. So when you choose large, generally there's only 2 choices. Some machines may have 3, but most of the time it's 2. So when you choose the focal spot, you're choosing which filament size is going to be used. Okay. And then the electrons must be stopped suddenly. When this occurs, what is that lost energy converted to? Mostly what? Heat. Mostly heat. Very little actual X-ray, right? So it's not very efficient, but it is what it is. It hasn't been able to be improved upon in all of these years. So most of that energy is converted to heat. That's why we have the insulating oil and the tube housing and those things to help protect us from the amount of heat that's created from that. So let's talk about some properties of X-rays. Just start calling some out that you can think of.
They're invisible.
Invisible, yeah. They travel at the speed of light.
No mask.
No mass. What? What else? Travel in what? Straight line. Have the ability to make some materials glow or fluoresce. Can cause damage through, yes, ionization. So these are just some of them that are in the chart in your Faber books. And we call most of those highly penetrating. We know that. And they can either be absorbed or they can also be scattered in the body, can cause biological damage, or electrically neutral. So I think we just talked about this. No, we didn't. What's the process of removing an electron from an atom called? Ionization. I think Jay did say that. What's another term for the many energies of the photons in the beam? Polyenergetic or heterogeneous, which means there's lots of different energies, and all of the photons are not the same energy. Okay. So when we talk about the radiographic qualities, we can sort of break those down into two big categories. We can talk about the visibility of details, and we can talk about the geometric integrity, or the recorded detail is an older term there. Spatial resolution, size distortion, shape distortion all fall under geometric integrity, because that means those things are affected because of the geometry of the beam, the way that the photons, come out of the tube and are directed at the patient. We know that they are what? Divergent, right? They do travel in straight lines, but they are diverged from the focal spot. Things that we talk about related to visibility of detail are going to be like the brightness of the image, the grayscale or the contrast, and the amount of noise that is in the image. So do you remember, hopefully, from first semester where we had 4 major categories in that first class, and receptor exposure was the first one that we really talked about. After we got through production and properties of X-rays and sort of introducing that material, then we started talking about these big categories. And so receptor exposure was the first one. So the definition of receptor exposure is just the amount of exposure that the IR receives. So it's not a measurement of patient dose, it's a measurement of dose to the actual IR itself. How much exposure made it through the patient and interacted with the IR. That's what receptor exposure is. So what primary factor do we generally use to control receptor exposure? Mass, yes. And what is the relationship between mass and receptor exposure? Specifically, directly proportional, meaning if mass doubles, then what happens to receptor exposure? It doubles. That's right. Reciprocity law just states that there's multiple combinations of MA in time that can equal the same mass. Okay, and therefore will give you the same IR exposure. So 50 mass should give you the same IR exposure whether you use 50 MA in 1 second or 100 MA at a half a second. It should still give you the same receptor exposure. So what is the formula for reciprocity law? Yeah, MA times time equals MAS. Yeah. So MA time and mass all have a directly proportional relationship to receptor exposure. We can break those down individually and talk about MA as being the current that's passing through, the tube at the time of the exposure, or that's being applied to the filament at the time of exposure. The exposure time is just how long is the actual exposure happening. And mass represents the total quantity of x-rays produced in the beam. So again, think about the paycheck analogy that we used to talk about, where your MA would represent your rate of pay and the hours worked would represent the time. And the bot, to figure out what your overall check is going to be, you have to put those two together to get the overall math. So just think of it that way. This is just a picture from your Faber book, and it's just showing you that if there's less mass directed at the patient, then it just makes sense that there's going to be less receptor exposure. If there's more mass directed at the patient, then there'll be more receptor exposure. So that's a pretty easy relationship to understand. Other influencing factors of receptor exposure we know are KVP, SID, whether or not we use a grid, beam restriction, filtration, the pathology of the patient, OID only in cases of what? When does OID affect receptor exposure? Only when we're talking about what? Yes, air gap, where we're talking about 6 to 10 inches of OID. If we're just talking about an inch or two of OID, we're probably not really going to see an effect on receptor exposure. But where we get into seeing it affect receptor exposure is when we have 6 to 10 inches of OID, and then it sort of acts as a low ratio grid. And then the patient themselves, the patient size. So we know that KVP has a greater effect on receptor exposure than mass does. So why don't we use KVP to control receptor exposure? Because it also changes what? Contrast. It changes the energy of the beam. It changes the penetrating ability of the beam. Therefore, it changes the subject contrast. So it changes the amount of scatter relative to photoelectric. So the reason that we don't is because it changes a lot of other things. But how much of a change in KVP does it take to double IR exposure? What do we say? 15%. So that's why we make the statement that KVP actually has a greater effect on receptor exposure than mass does, because it only takes a 15% change in KVP to double or half receptor exposure. Whereas with mass, it takes what percent to double or half exposure? Yeah, 100%. Yeah, it takes double. So, all right. So the 15% rule just states that if you need to increase contrast, but your overall goal is to maintain receptor exposure, then you would decrease KVP by 15% and double the mass. So remember that KVP has an inverse relationship to subject contrast. So if KVP goes up, subject contrast goes down, and vice versa. The rule of 10 is just stating that between the KVP range of 60 to 90, that 15% is about 10 KVP. So it's just a way to easily do the math. So if I went from 60 to 70 KVP, I could just half my mass. As long as you stay within that 60 to 90 range, it keeps you pretty close. With KVP and IR exposure, if you have lower KVP, then most of the photons are going to be absorbed, and they're going to be fewer to actually make it through the patient and interact with the IR. If you have higher energy, there's going to be, number one, if we increase our KVP, two things are actually happening. All right. So what did we say happens in the tube when we increase our KVP? More what?
Photons.
Yeah, more photons are created to begin with, right? So in the tube itself, there's just, because the energy or the speed of the electrons increases, there's going to be greater impact at the anode. Therefore, there are going to be more photons produced to begin with. And of those photons, they have higher penetrating ability. So there's a better chance that they're going to make it through the patient and interact with the IR. So it takes into account both of those things when you're talking about making adjustments to your mass when you change your KVP 15%. Y'all, is that coming back? Remember that? Okay, good. I know I'm going fast, but stop me if you have a question about something and we'll try to address it. I just want to make sure we can get through it all. SID and inverse square law. So that states that the intensity of radiation is inversely proportional to the square of the distance from the source of radiation. So how do we write that as a formula? It doesn't matter if you put like your old, new, like if you use new and old, or if you use 1 and 2, or whatever, as long as you keep it in an inverse relationship. So inverse square law is talking about what compared to distance? Intensity, I. So inverse square law is looking at intensity. So you have to keep that distance and intensity in an inverse relationship, because as distance goes up, what happens to intensity? It goes down, and vice versa. So it doesn't matter how you write it, as long as you keep intensity and distance in an inverse relationship. All right, and these are just, again, some pictures to help you see how the intensity changes because of the divergence of the beam with the change in distance. So exposure maintenance formula is derived from the inverse square law, and it's looking at changes in mass. How do you have to change your mass when you change your distance? And so it is also called direct square law, because it has what kind of relationship to distance? A direct relationship, which means if your distance goes up, your mass has to go up to compensate. If distance goes down, your mass has to go down to compensate. And it's by a factor of the square of the distance. So that's important. Again, it doesn't matter. This thing changed the format or the way this was laid out. It didn't look like that originally. I don't know why it's all jammed up down there, but anyway, again, it doesn't matter as long as you keep mass and distance in a direct relationship in the formula. Remember, I always like to use the new over old. To me, that's the easiest way to solve for it. So I always put my new mass, because that's what I was looking for, X over my old equals my new distance over my old. That's just an easy way to solve for it. So, but again, it doesn't really matter as long as you keep it in the right relationship. So if your original mass was 10 when using 36-inch SID, what would your new mass be if you use 72 inches? So first of all, would you need more or less if you're going from 36 to 72? More. Now we can do this math in our heads, for real, right? Because what is the distance doing? Doubling. So if the distance is doubling, how much more mass do I need? Four times. Because it's to the square of the distance. 2 squared is 4. So I would need 4 times as much mass at 72 inches that I needed at 36. So I would need 40 mass. And then the opposite would hold true. If I had started out at 40 mass and was going from 72 to 36, then I would need a fourth of the mass. So I would need 10. Okay. Speed class. Okay. So this can be a difficult concept for people who weren't brought up on film to understand film screen. It was a lot easier to understand then. But speed class is just basically saying, okay, how much exposure is the IR looking for to have a good quality image based on exposure and patient dose, okay? So 100 speed class is generally looking for 2 MR to the IR, all right? 200 speed class is looking for 1, and a 400 speed class is looking for half. So the higher the speed class, the less radiation. When I say looking for, meaning like when EXIs are being developed, right, or set, then it depends on what speed class your system's operating at. Most of them are going to operate at about a 200 speed class. So it's going to be generally in other words, 1 MR, when you're operating at a 200 speed class, 1 MR is the amount that the system is looking for to give you your exposure indicator as being right on target. Does that help? That makes sense a little bit? So let's see if I have another slide on here. Okay, yeah. So if a system is operating at a high speed class, meaning like a 400 speed class, what might you see in your extremity images? Because it's not looking for as much radiation, you might see what? Noise, right? Because we're already using such small mass values for distal extremities, right? You think about the mass values that you're using for fingers, hands, toes, feet. It's low, right? Probably not much more than 2 in most cases. A lot of times it's 1 or 1.5. So if you're operating at a high speed class, then it's not going to take as much mass to give you 0.5 MR. Therefore, you might see some noise in those images. So let's see, the speed class you choose to operate is dependent upon the amount of noise you're willing to accept. So this is something that's done through the physicists, maybe your service engineers, your radiologists. How much noise is your radiologist or your ordering physicians, like if you're talking about at a Steadman Hawkins or Piedmont, how much noise are they willing to accept? Right? And then they would probably determine that and set their speed class. So speaking of that, so of these, just to make sure, so of these 3, which speed class do you have to use more mass on? 100, because it's requiring a higher dose to the IR to be acceptable. That makes sense? So if you operate at lower speed classes, what does that do to your patient's dose? It increases it. But again, it's all related to how much noise is whoever's got to look at these images willing to accept.
How do you know what the speed class is?
That would be something that like your whoever's responsible for your equipment, like the testing of your equipment and stuff, would have that on record somewhere. We used to be able to, with CR, we could change the speed class by changing, I don't know if y'all remember or not, you probably don't, because we didn't use CR a whole lot with y'all, but on the reader itself, there was 2 little buttons at the top, and one had a hand, and one had, like, I think it was a chest. And depending on which one of those you selected would determine the speed class that cassette was going to be read at. That makes sense? But now, in general, you can pretty much assume that most of your operating speed classes are the 200, sort of just in the middle. But that's a good question. I'm trying to think of who specifically, like, maybe your, if there's like a QC tech. They used to have a QC tech at Memorial, like there was a separate job. They took care of all of the testing and all that for the equipment. I'm not sure if they still have a person in that position or not, but somebody that's related to tracking the equipment and all that kind of stuff that deals with the physicist would probably know. Okay, grids. So I know that grids can be, matter of fact, I think Christy said that she had some discussions about grid stuff again this week, trying to help people understand, because it is important. Like, it's important. There wouldn't be different orientations of grids if it didn't matter. That's what never made sense to me, for people to say, I'll just grab one, it doesn't matter. Well, there wouldn't be a long dimension one and a short dimension one if it didn't matter. There would have just been one, right? So grid ratio, there's a lot of definition stuff with grids. So grid ratio of the height of the lead strips to the distance between them. Grid frequency, how many strips are there in a given distance or unit of length. As the grid ratio increases, what happens to IR exposure if you do not compensate with your mask? Does it go up or down? Down, because we have to do what to our mask when we either go from not using a grid to using a grid. We have to increase it. And if we don't, then our IR exposure is going to go down. So it decreases. Why?
The x-rays have to penetrate the grid to get to the IR.
So the grid is doing what? It's absorbing, right? So hopefully it's absorbing all of the what? Scatter. But it also absorbs part of the what? Primary, which is not ideal. We try our best to minimize the amount of grid, and that's called what? Grid cutoff. So anytime part of the primary beam is absorbed in the grid, that's called grid cutoff. We try to keep that to a minimum, but I can't remember what all I have in here. So the grid does absorb some of the primary beam and also prevents scatter from reaching the IR, which decreases overall IR exposure. So even though scatter is unwanted, it is a part of receptor exposure. Like it does make up part of the receptor exposure. So as the lead content of the grid increases, the ability of the grid to remove scatter and improve contrast increases. That just makes sense. Also makes it a little less forgiving, right? As the lead content goes up, it means you have to be a little bit more careful about how you use the grids. Yeah, I want to make sure I had this in here. So there's some common grid errors. Grid cutoff, again, is the unwanted absorption of primary. That can happen if we use the wrong SID. So that's focal range, grid focus. That's talking about the same thing. That is an SID that's supposed to be used for that particular grid. And if you don't use an SID in that range, then you can get grid cutoff. If the tube is angled against the grid lines, you can get grid cutoff. If the grid itself is at an angle, so like, for example, if you have a patient that's in a bed and they come to you for an abdominal series or something, and you put y'all are grinning, does that happen? Does that happen recently or something?
Actually,
and if that grid is at a tilt and it's tilting against the grid lines, you are going to get grid cutoff. Your exposure indicators are going to indicate that you are underexposed, even if the mask that you used should have worked for that patient. If you're not using your grid right, then you can keep on adding math and keep on adding math, and it's not going to fix a thing if you don't correct the mistake that you're making with the grid. Also, if the tube is not centered to the grid, and you say, well, I would never do that. Why would I do that? Well, we do it, and I'm not trying to, I just can't stand when I can't see everybody. I'm not trying to like focus on you. This is like, I keep trying to make sure I can see you. Right? You're putting the grid underneath maybe a very large patient, and you are guessing where it is. Let's be honest, right? You're trying to reach under there. And I mean, I used to, even when it was really big patients, and I mean, I used to even like stick my hand in underneath them and feel where the edge of it was and like mark it on my arm and go around to the other side and put it under there and see if it was equal. I mean, you try everything, right, to try to get the grid right and under them in the center. But sometimes it's off. And it's easy to line your light up, right? Because you can see exactly where your light is on your patient, but not so easy. So that's how that can happen. You can accidentally not have your grid centered and get what's called lateral decentering. And then again, when you're laterally decentered or you're using the wrong SID, what's happening to how the tube is directed at the grid with the divergence of the beam? What's happening? If you're not centering right to the center of the grid, or you're using the wrong SID, Is it matching up? No. So it prevents the natural divergence of the beam from matching up with the way that the grid lines are focused in there. Because remember, they start out on a focused grid, they start out perpendicular right in the middle, right? And as you move out to the edges, what's happening to them? They're beginning to tilt so that they match the divergence of the beam. When that no longer matches up, then the grid acts almost like a funnel, isn't a great word, but they're not matching up. So the lead strips are absorbing a lot of the primary that shouldn't be being absorbed. So the grid being placed upside down is not something that's going to happen real commonly now, because we have the grid caps and there's only really one way to put the receptor in there, and you're not really going to flip it upside down, hopefully, unless you just are having one of those days where nothing's going right. Any questions about this? Okay. Grid conversion factors, you just got to memorize those. And I'm trying to just keep up with what time it is so it can be on the lookout for Pamela. All right, let's talk about beam restriction and IR exposure. So we know that the size of the field, the size of the collimated field, does affect IR exposure. And so when we ask the question, what happens to IR exposure if you go from using a 14 by 17 field size with a particular mass down to an 8 by 10 field size? So let's say that we go from a 14 by 17 where we're doing a lumbar, and we go down to an 8 by 10 where we're just doing a spot, and we don't change our mass. What's going to happen to IR exposure? Is it going to go up or down? I heard down and I heard up. Who votes for down? Nobody wants to vote. That's okay. So, IR exposure, wait a minute. I read that to y'all wrong. I'm sorry. Let me read it again. What happens to IR exposure if you use a 14 by 17 field size with the mass for an 8 by 10 field size? So I've said it backwards. I'm so sorry. So let's say we started out with our spot 8 by 10 and we used a particular mass for that. And then we did our AP 14 by 17 and we didn't change our mass. Then our IR exposure would go up because we don't need as much mass with a bigger field size. I'm so sorry. I read that wrong. Why? Why don't we need as much mass with a larger field size than we do with a smaller? More matter, more scatter. And even though scatter is unwanted, it is a part of receptor exposure. So because there's going to be more fog, we call that exposure that we get from scatter is basically puts like a fog on the image. And so there's going to be more chance of scatter on the image, which does contribute to receptor exposure. So if we did the opposite, if we go from a 14 by 17 down to an 8 by 10, then we have less matter, we'd have less scatter contributing to receptor exposure. So we'd have to increase our mass to compensate. Sorry about that. No wonder y'all didn't want to answer. I've questioned two different ways. You got to remember your multipliers. So basically, this is just saying you need about 30% more when you go to a 10 by 12 and about 50% more when you go to an 8 by 10. Filtration and IR exposure. So what does increasing filtration do to the overall IR exposure? It decreases it. And the why is because initially when you're adding filtration, you're just going to filter out those very low energy photons that aren't going to do anything for you. They're going to do what, basically? Be what? In the skin dose, right? They're just going to get absorbed in the patient's skin, increase the patient's dose, do nothing for us as far as our image goes, okay? But as we increase filtration and we maybe keep increasing filtration, then we might begin to filter out some of the image forming photons. So there's not a formula, there's not a multiplier, anything like that, that says, hey, if you use this much filtration, you got to increase your mass this much. So you just need to know that in general, if you get to a certain point of adding filtration, you may begin to see a difference in your receptor exposure. I don't know if y'all remember us doing that in the lab, but we did. We had the little wheel and we turned it and kept increasing filtration, and we could see our EI number going down, down, down every time we did that. Now, here's where we're talking about air gap, and we sort of addressed this already a few minutes ago, but OID only affects IR exposure when you're using an air gap of at least 6 to 10 inches. So if we do have an air gap of say 10 inches, would IR exposure go up or down? Somebody said it, down. It'll go down. Why? Because the scatter is going to be what? Yeah, missing the IR, not reaching the IR. It's hopefully, that's why you do an air gap, is so that the scatter will miss the IR. Now we have a naturally built-in air gap for lateral C-spine. That's why, like, if you're doing a cross-table lateral C-spine, you don't really have to use a grid. You don't have to do it at the wall bucky. You could just put your IR up beside the patient because that acts as a very low ratio grid. But you know, it's not wrong to do it at the wall bucky. And I don't know, do y'all even still do like the trauma cross table laterals on people, or they sort of had quit doing that because they were just clearing people clinically or sending them to CT. And we sort of got away from that. We used to do them on every patient that came in with a C-collar on. Every single one of them, we had to get cleared. What a nightmare. Okay, and then we talk about pathology and IR exposure. So if pathologies decrease IR exposure, they're said to be what?
Additive.
Yes. If pathologies increase IR exposure, they're said to be destructive or subtractive. Yes. So when we think about additive pathologies, think of it this way. An additive pathology means you have to add technique, okay, because it's adding either to the thickness of the part or it's adding to the atomic number of the part. If it's subtractive, then you can subtract technique. Now, books don't agree on any of that either, okay? One book says if it's additive, increase KVP. If it's subtractive, decrease KVP. I mean, there's literally three different books say three different things. So the bottom line is, with pathology, that's going to come with experience, you know, you seeing, okay. And if the pathology is not really that advanced, you're probably not going to really have to change your technique, especially with digital, you know. So anyway, your patient size. Thicker patients require more mass to maintain IR exposure for a given body part. That doesn't make sense. Think about it. If you have a part that's this thick, you're going to use one mass. If you double that part thickness and you don't change your mass, what's going to happen? Yeah, it's going to be underexposed, right? So you just, and we learned, I don't know if I have that in here or not, maybe, no. Do you remember what change in part thickness it takes to need to double your mass? Anybody remember? 4 to 5 centimeters of part thickness change. But I think what y'all are thinking are maybe the thickness requirements for using a grid. That's 10. That's 10. So it's 4 to 5 centimeters. If it's a 4 to 5 centimeter change in part thickness, then you really need to double your mass, or vice versa. Contrast. Okay, so now, phew. All right, we're through the first one. Gosh, how long did that take? Contrast, we know, is the difference in adjacent brightness levels on an image. What is the controlling factor of subject contrast? KVP, yes. When you increase KVP, what happens to subject contrast? It decreases. It's an inverse relationship. Why? If you increase KVP,
straight through, it's not going to be absorbed. It's not going to be long.
wait a minute, say again.
If you use more, it's going to blacken it. You can't see because it's not going to absorb.
Everything's getting more uniformly penetrated, right? Because when we increase KVP, that means the energy of the beam is increasing, which means the penetrating ability of the beam is increasing, which means there's a better chance that the photon is gonna make it through, which is what you're talking about. So your part is getting more uniformly penetrated, so all those brightness levels are sort of coming closer and closer together. And then what were you saying, Deanna? Because I think what you said was making sense too.
I just said more penetration.
Yeah, yeah, more penetration. So, so that is why subject contrast decreases as you increase your KVP, because it's just getting all more. If every single photon got through, we would have zero contrast, right? Hopefully y'all remember doing that on that ImageJ software too, but anyway. Let's see here. We just talked about that. So this one is important. I don't know if you've noticed yet, if you've worked on any of the questions, they like to ask questions and have these and then say A, B, D, and G is the answer, or B, C, F, and H. Have y'all got to those questions yet? The contrast ones, they want you to know all the different ways to describe and talk about contrast. So when we talk about high contrast, what kind of description is that if it's high contrast? Black and white. If it's high contrast, that means there's a lot of difference between the brightness levels. So high contrast would be like, the highest contrast would be totally black and totally white. Just the most difference, right? What do we talk about when we talk about high contrast? So we said that's very black and white. What kind of scale is that? Short scale. It's either black or white. Very few shades of gray. What kind of KVP gives us that high contrast? Lower KVP, right? Lower KVP. And then what kind of exposure latitude? Oops, sorry. What? Oops.
Narrow.
I had it one at a time.
I think it's narrow.
It's narrow, yeah. So the opposite would hold true for low contrast. Description would be what? Lots of shades of gray. Long scale. Remember, low, LO. So low contrast, lots of shades of gray, long gray scale. What kind of KVP gives us that? Higher. And then it gives us what kind of exposure latitude? Wider. Yeah. Okay, so make sure that you understand the different descriptions of contrast. Now, when we talk about all of those things, we can put the word subject contrast in there because that's basically what we're talking about. Because now, when we talk about display contrast, what controls the display contrast of the image? Huh? The computer, right? It depends on what lookup table was used. It depends on whether or not you want to change the brightness and contrast on the image. In this case, contrast. You can make it look however you want it to look, right? With the computer. But subject contrast is the contrast that we get because of the way the photons are either absorbed or not absorbed by the patient's body. Finding a way, okay. So, subject contrast, radiographic contrast caused by the differences in the composition of the patient's body tissues. Tissues absorb X-ray photons differently due to the tissue density, which is determined by the average atomic number and how compact the atoms are. What's the term for this? When tissues absorb radiation differently. Differential absorption, right? It's in the name. Tissues absorb radiation differently. And subject contrast is controlled by what did we say? KVP. Because subject contrast will change depending on if you're using really high KVP or really low. We talked about the three fates of a photon. Poor little things. What's the fate? What are the three things that can happen to a photon when it's delivered? So absorbed, penetrated, or scattered. Yes. So they can be transmitted through with no interaction at all. They can be photoelectrically absorbed in the patient, or they can be Compton scattered. What is the term for the reduction of the radiation intensity due to either photoelectric and Compton? Look at Katie still walking out. Attenuation. Yeah, she knew it. That's the answer. So attenuation is not just absorption. It's loss of intensity to either absorption or scatter. It's a loss of that initial amount of intensity that's being directed at the patient. How does increasing collimation? So you got to ask yourself, if I'm increasing collimation, I am collimating more, which means the field size is doing what? Getting smaller. So when I reduce field size, how does that affect contrast? It improves it, right? It increases, it goes up because, yeah, that's right. Because less scatter is produced, which always increases contrast. Anytime scatter makes it to your IR, that's a decrease of contrast and that's unwanted. So low contrast in and of itself is not a bad thing always. Sometimes we want low contrast, right? We don't want real black and white. In some cases, if the contrast is super black and white, we miss stuff, right? We miss those subtle changes in brightness. But anytime contrast is reduced because of scatter, that's degrading to the quality of the image. So the purpose of the grid is to keep scatter from reaching the IR. It does not affect the production of scatter. Same amount of scatter is going to be produced. It just changes what actually makes it to the IR. So using the grid or a grid with a higher grid ratio does what to contrast? It goes up. It improves it, right? That's really the primary purpose of the grid, is to improve the contrast. If you, let's see what else I have here. Hold on. Let's get a reason. So I know that now there's some virtual grid software out there, and I get that. There's also grid replacement software, so I understand that. I know that with these new pieces of digital equipment, you don't always have to use a grid like we used to. Oh, let me see if that is our, let's see, let me pause this real quick. Okay, so I think finished talking about grids and contrast. What I think I was saying was, when I realized she was standing there, was that a grid improves contrast. That's the main function of it. If you do, we were talking about virtual software and all that, virtual grids, and so there is some software out there that can replace using a grid. There's also software that can help improve, like if grid lines are showing up, like trying to sort of subtract those out of the image. So there are some other things, but I mean, I would just say in general, if you have a really large patient or an abdomen, I wouldn't depend on that, grid line. Gosh, I'm sorry, I'm blanking on what it's called. What? Smoothing? It's sort of like smoothing. Anyway, that's not the word, but it's sort of like that. I wouldn't depend on that. I mean, if it's a large patient and you're trying to do an abdomen, you really need to use a grid. Because you can even see it on smaller people. If you don't use a grid, the contrast is so low inherently in the abdomen anyway, that if you have that added scatter on there, you just may as well not even do it a lot of times. So, all right, filtration and contrast. Increasing the filtration is said to harden the beam. What does that mean? What does hardening the beam actually mean? Yes, so it's removing the lower energy photons, which does what to the average energy of the beam? Increase. That's right. So for contrast, when you increase filtration, it has the same effect that increasing the KVP does, right? So because it filters out the lower energy photons, which is what Ebby was saying, increases the average energy of the beam, which has the same effect. So there's multiple ways that you can increase your test average, right? You can do what?
Do better.
Do better, right? You can score higher. That's one way. So that'd be like increasing the KVP. Or if the teacher is nice and they drop the lowest test score, that also increases the average of your test. So that's the same thing that filtration does. It's just increasing the average energy of the beam by taking out those lower photons. So there's two ways to harden the beam, and that's what this is talking about here. This is from your Bouchon book. So again, it just demonstrates that as you add filtration here, what happens to the X-ray emission spectrum, meaning the quantity and then the quality, which is plotted on the x-axis. So you can see that as you add filtration, quantity decreases, however, quality increases because it shifts slightly to the right. Again, back to air gap. So if you have a 10-inch air gap, what would that do for contrast? It acts as a low ratio grid, so what would it do? It would increase contrast. And again, it's for the same reason, because the scatter is what? Not hitting the IR. Hopefully it's missing it. So it's for the same reason that it affects receptor exposure and contrast, but in different ways. So it reduces receptor exposure because the scatter is hopefully missing, which improves the contrast because the scatter is hopefully missing. So, and that's just a picture of what is supposed to be happening when you use air gap. So, as far as talking about the patient in contrast, to have contrast, you have to have some photoelectric absorption and transmission. So if you had either photoelectric and transmission, that would give you the highest possible contrast you could have, right? Either the photons are being absorbed or they're not. That would give you the highest contrast. Subject contrast is caused by the difference in the composition of the patient's body tissues. So again, it goes back to things like you're looking at the thickness of the part you're talking about, or the average atomic number of the part, or how densely packed the atoms are together as to whether or not you get a photoelectric interaction. And I think y'all are probably going through a lot of that in Ethan's class this semester. Are y'all talking about the photoelectric absorption and probabilities of it? And okay. All right. So now we've talked about receptor exposure, we've talked about contrast. Now we're going to jump to distortion is the big category, and we had size and shape under distortion. So size distortion is pretty simple explanation. It's just misrepresentation of the true size of the object when you compare it to the size of the image as compared to the object. When we talk about size distortion, we're always talking about magnification. So we can't have minification, right? Just based on the geometry of the beam. I'm not talking about minifying with the computer. I'm talking about we can't have the image be smaller than the object just based on the geometry of the beam. It can't happen because the beam is doing what? Diverging, spreading. So there is no way we can have minification. So when we talk about size distortion, we're talking about magnification. The distances that affect that are your SID, your OID, your SOD. And we know that these formulas are just based on if we have 2 out of the 3, we can figure out the third. SID is made up of the source to object plus the object to image. That makes up your source to image. What is the major controlling factor of magnification? Which of those distances is the major controlling factor of magnification? OID, yes. I don't know if you remember, but it took very little OID in the lab to really see a difference in the magnification on the image. So as OID increases, what happens to magnification? It increases. The more OID you have, the more magnified that image is gonna be. And this is just pictures from your Faber book again, demonstrating the difference in the amount of object to image distance, how it changes the amount of magnification in the image. The closer the object is to the IR, the better, or the least magnification you're gonna have. So how does SID affect magnification? So if we increase our SID, what happens to magnification? It decreases. Again, always go back to chest x-rays. Why do we want to do chest x-rays at 72 inches whenever possible? Well, it's to reduce magnification of the part. And it also, we're going to talk about in a minute, gives us better spatial resolution. Yeah. And then again, just another picture there to help you visualize. So magnification factor tells the radiographer how much larger the image will appear as compared to the object. And if you remember magnification factor, we can figure that out by putting SID over SOD, which is typically what we're going to do because we know those distances, right? Generally, we know SID, or we can figure out what SOD is based on what our OID is. Or if we have the if we're actually measuring the image and we have the a known object size, and we can also figure out magnification factor that way. Where does this come into play? What kind of clinic sites is this important in? Ortho. Who said it? Ortho. When they're doing like what? Hip replacement, joint replacements. That's when they put that ball, that metal ball, into the image because that is a known size, right? That is something of known size. So that helps them determine what size hardware they need to use because that stuff is expensive. You don't want to be opening up even a screw or something that is going to be too long or too short because somebody's got to pay for that and it's not cheap. So that's why they do that. You can also calculate percent of magnification just by you can write the formula. Now, there's 3 different ways to write that formula. This is one way. Take your image size minus your object over your object times 100. You could also write it as image size over image size minus, image size over object size minus object size over object size times 100. It's the same thing. Or you could say magnification factor minus 1 times 100. It's all talking about the same thing because anything, image size over object size is what? What did we just say? Image size over object size is what? Magnification factor. So if we wrote it that way, image size over object size, that's magnification factor. What is anything over itself? 1. So that's why I'm saying magnification factor minus 1 times 100 is the same thing as this. This again is just showing you how you can, and the magnification is based upon the law of what? What do we call that? The law of what? Similar what? Similar triangles, right? It makes triangles, right? So this would be one triangle, right? This would be a similar triangle because they share a angle. I don't know if y'all remember all that. Anyway, that is where that's derived from. So we talked about size distortion, meaning magnification, and we can use data by using magnification factor or percent magnification to talk about the difference in the amount of magnification in the image. Shape distortion. How did we say that shape distortion is created? Through the relationship of what?
Angle of the patient object and the IR.
So it's the object, the IR, and the part is the object, the central ray, right? So the CR, the part, the IR. There's an ideal relationship that needs to be maintained if we are to minimize shape distortion. So that is by placing the object parallel to the IR. So if this is my IR, we want the object parallel, right? We don't want it tilted up unless we're purposely doing it or an oblique or something. We want the central ray to be what? Perpendicular to both the object and the IR. right? And then what's the last relationship? Well, that was it. Central ray perpendicular, sorry. Central ray perpendicular to the object and the central ray perpendicular to the ion. And that gives you the least amount of shape distortion possible. Foreshortening is created how? By angulation of what? The part, the person, the part. That's how you get foreshortening. When the object is not parallel to the IR, but the central ray is. So again, foreshortening just means that the image looks shorter than the object actually is. What about elongation? That is when images look longer than they actually are. So how's that created? Angulation of the central ray or of the IR. Yeah, both of those will give you elongation. So we know that that person's humerus did not look like that, right? And you can see that when the IR is tilted, see how it does actually create more OID between that end of the part, and that's why that end of it looks so gigantic. It almost looks like a carnival mirror. If y'all remember us talking about, which we're going to talk about fluoro in a couple weeks, remember the distortion that we get based on the input phosphorus curve. It can give us some pin cushion looking distortion. So it's similar. Spatial distortion occurs when either the part is rotated away from parallel or the central ray is adjusted to purposely separate superimposed structures. So when we have structures that are lined up directly on top of one another, for example, the sternum. So you have the sternum, and then you have the mediastinum, and then you have the spine, and all of that is stacked up on top of each other. So when we purposely want to see those structures separated, we call it spatial distortion. So in the case of the sternum, we rotate the part to separate superimposed structures, right? Because we do the RAO, and that sort of throws the sternum off the spine, so it's not superimposed in the spine. Or if we think about the skull, I know y'all don't want to, but let's think about the skull. The town projection, what do you do on the town with the central ray? You angle, right? Either 30 or 37, depending on which baseline you're using, right? OML or IOML. But typically, if you don't do that, then you have orbits in the middle structures and in the back of the skull, all superimposed, right? But when we throw that hard angle on there, what happens? Everything separates out, right? The mandible gets thrown down, your orbits get thrown, everything gets thrown down off, and then you can just see the skull itself. So one thing to remember, the structure that is furthest from the IR is going to move the most and in the direction of the angulation. So remember the A, B, C stacked up. If it's A, B, C, then A is going to move the most because it has the most OID. Anything that's further from the IR is going to move the most, and in the direction of whichever way you're aiming. Spatial resolution. So now we have done 3 of the 4. This is the last big category of quality factors. So spatial resolution is just defined as, well, there's several different ways that books define it, but the sharpness of the structural edges recorded in the image. So how well can you see those structural edges, like the lines in the image? Resolution is the measurement of recorded. So recorded detail is just that, is what is actually recorded in the image. Recorded detail comes from the things that we know to be true about the geometry of the beam, right? So SID, OID, SOD, focal spot size, all of those things are what is actually recorded in the image. Resolution means, can we see 2 adjacent structures as separate? So if you had, and I don't know if y'all remember the picture from the PowerPoint, in one image, it was showing a rectangle. And it really was two parts to it. There was a separation between them, but it imaged looking like it was all one part, right? In a poor resolution image. In a higher resolution image, you could see both parts of that rectangle as being separate. So the resolution would be better in the image where you can actually see that adjacent structures are separate and distinct. Okay, everything that goes into creating the image is going to affect your resolution. So not just the geometric factors, but also your visibility factors, right? So whether or not you have a lot of fog in your image, or whether or not you've overexposed it to the point where there's saturation in there and now we can't see the recorded detail, right? Because we've blacked it out, we've saturated it. So everything that goes into creating the image affects resolution. We can measure this with a resolution test tool, line pairs per millimeter. Do y'all remember looking at that and trying to see how far down you could see? That is still very subjective, right? Because it's based on what? Yeah, whoever's looking at it. And whoever has good eyes is going to see further, and those who don't have such good eyes are not going to see as far. So that's still subjective. Your geometric factors that we just alluded to here a second ago, focal spot size, SID, OID, they affect spatial resolution, the recorded detail in the image. So we know that we get less spatial resolution with larger focal spots, right? It improves with smaller focal spots. If our X-ray machines were a point source where there was only one spot on the anode that the photons were created, we would have perfect spatial resolution, right? But we don't. It's an area, right? So some of the photons might be created on this part of the target and some might be created down here, and they're going to see the object differently. Remember this? Remember doing this? Like, I'm going to hold my finger up in front of Deanna's face, and I said it right. So if I have looking at her with my left eye compared to my right eye, what happens to the perspective that my eye is seeing? It changes, right? So that's what's happening here. So just remember that small focal spot gives you better spatial resolution. Think back to the examples of paintbrushes. If I'm just concerned about just getting some paint on that wall, I'm going to use either a large brush or a roller. I'm not real concerned about the details, right? But if I got to paint that corner over there where it's white to green, what am I going to do? A small brush where I can get really good details, pull that brush down through there. So same thing, you can think of it that way if you get confused about which is which. SID and spatial resolution. So the greater the SID you have, the better the spatial resolution you're going to have. Again, think back to, okay, the two reasons why we want to do chest x-rays at 72 inches. Decrease magnification and improve spatial resolution. OID. Also, as OID increases, what happens to spatial resolution? It decreases. So not only does it increase magnification, it also gives us worse spatial resolution. So just another reason that we want to try to keep our part as close to the IR as possible whenever we can. So unsharpness and spatial resolution, remember this seems very counterintuitive to talk about something being unsharp, but that's the way it is. They have an inverse relationship. So as unsharpness increases, meaning it gets more unsharp, then what's that do to spatial resolution? It decreases. It's an inverse relationship. And we have unsharpness formula that we can use just to sort of arbitrarily talk about the unsharpness of one image compared to another. All right, so focal spot size times OID divided by SOD gives us unsharpness, and we can look at those numbers and compare. So again, if unsharpness goes up, spatial resolution is going down. If it becomes more unsharp, which I know that sounds so weird to say, but if something is getting more unsharp, then that means it's getting less sharp, which means spatial resolution is going down. Any questions about that? I know I feel like I'm just blah, 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 going really fast. Okay. The home stretch here, just a few more slides. All right. The most detrimental effect on spatial resolution of an image is motion. It can be voluntary or involuntary. So voluntary would be what? Something the patient can control, like they move, like they physically move. It could be breathing, right? They can control breathing unless they're on what? A ventilator. And then it would become involuntary because it's breathing for them. They can't control it. An example of involuntary motion not related to that would be what?
Peristalsis.
Peristalsis. We can't control that. Be nice if we could, right? Sometimes, but we can't. So the most effective ways to prevent motion are number one, what? Short exposure times. That's the best way. Other things are giving clear instructions to the patient, being very clear what you need them to do, immobilization of the patient if it comes to that, especially with children, because you can't rationalize with them a lot of times. You can't, they think that you're going to give them a shot, right? When I went to the doctor as a kid, I thought I was getting a shot every time I went. And so I got ready. I was awful. They'd have to have 5 people hold me down to get a shot. So it's important to immobilize. All right, the last thing that we're going to talk about here related to pretty much first semester. This review has been all first semester mostly. Is AEC. And I love AEC, but I know everybody does not share that love. Automatic exposure control, right? It's just a way that a predetermined amount of signal or charge has to be met for a signal to be sent to the timer circuit to cut the exposure off. So once that predetermined amount of charge is met, the signal goes, it cuts off, and it takes away your responsibility to set what? Specifically, max, right? So you're still having to set a KVP. You're still having to select the photo cells, right? You're still having to select a density setting, but you don't have to worry about the mass value. What else do you have to worry about, though, that is like super important when you're using the AEC? Yes, patient positioning over the cell. If you don't position well and your exposure doesn't come out good, it's not the AEC's fault, right? The AEC gets blamed for a lot of stuff. It's not the AEC's fault. It's our fault for not positioning well. So let me ask you this. And I know that you don't most of the time have the ability to change the MA station. Some manufacturers do, like our new Siemens, we don't. We can't set the MA at all. But if we could, and we increased our MA station setting, what would happen to our exposure time? Would it go up or would it go down? If our MA is going up, it's going to go down, right? Because it's not going to have to stay on as long, right? If we take our MA, let's say from 200 up to 400, then it's just not going to have to stay on as long because the current is higher. It's going to reach that preset charge quicker and cut off quicker. Our overall receptor exposure is going to do what? Stay the same. That's the goal of the AEC and part of the beauty of the AEC. All right. Let's talk about KVP. If the KVP, if we're setting up the control panel and we go from 70 KVP down to 60, make sure I'm reading it right. So we're decreasing. What's going to happen to our exposure time? Is it going to go up or down? It's going to have to go up, right? Because it's going to take longer for that preset charge to get met than if we used 70. So remember, the IR exposure is going to stay the same. It's just going to be changing the time of the exposure. So the AEC, just remember, is doing what we would do to the technical factors were we manually setting them. So think about it. If my goal is to keep the same receptor exposure and I decrease my KVP from 70 to 60, what would I do to my mask? I would double it. Well, the AEC is doing that through changing the time. Yes, because the AEC is controlling the time of the exposure. How, let's see. The only way to change the overall IR exposure when using the AEC is to use the plus or minus density setting. Purposely, intentionally. Let me add that word. I probably need to add that in there. The only way to intentionally change IR exposure is to use the density settings. We can mess up, right? And we can unintentionally change IR exposure by doing what? What's one mistake that we can make that would change IR exposure and not, our image quality would not be good?
Wrong photo.
Position, yes, both. So choosing the wrong photo cell is one thing, or not positioning over the photo cell or photo cells that we have selected. Both of those things can make us unintentionally change receptor exposure. So let's say, I think I have an example. Okay, so if we're doing an AP knee, all right, we would want which photo cell to be selected for an AP knee? The middle, the center one, right? So let's say we accidentally have the outer photo cell selected. What's going to happen to our IR exposure? Is it going to go up or down? It's going to go way down, right? Because here's our, so we have our knee right in the middle, right? But this photo cell out here is selected. Is there any anatomy over there? No. So that preset charge is going to be met super quick. It's going to send the signal to the timing circuit to cut off too quick. Therefore, the knee area that we want to see is going to be way underexposed and noisy. And so more than likely, we're going to do that over. Don't be sending images that have terrible noise in them. Y'all know what noise looks like. We'll talk more about that when we go over digital. But look at your EXIs or your EI numbers or your S values or whatever. Don't be sending noisy images. Because remember what I said, if they look noisy to you, what they gonna look like to the radiologist? Worse, much worse, because their monitors are much better than ours.
Yeah.
All right, let me stop this recording real quick.